Hello and welcome to Always Be Better with Mel Wyndham. Today we're going to try a little experiment. But first, during this exciting election year, we're going to explore popular statistical argument. Let's see, from 1980 to 2016, we've had 10 elections. And out of those elections, 19 counties, they voted for the candidate which ended up winning the presidency. In other words, all 19 counties, 10 times in a row, predicted the president. That sounds amazing. We don't know what is special about these counties. Maybe they're purple so that they capture the national trends better than any other county. All we know is that they are very good at selecting the president. But in 2020, something strange happened. 18 of those counties voted for Trump, and he lost. So that means only one county got it right 11 times in a row. Now, that is such a statistical anomaly. Many say that this is evidence for fraud. So I'll show you the math in a little bit. But first, we're going to perform our own experiment. And I ask you to watch it till the end. I promise you it will be worth it. Well, here I am with my family, and we are about to simulate bellwether counties. But instead of counties, we're going to be using pennies. Check this out. I have 1,000 freshly minted pennies, never before opened, and ready for us to test. We are going to look for biased coins. Let me explain that. We usually expect a penny to flip 50% head, 50% tails. So if we were to flip it 10 times, we would expect 5 heads, 5 tails. But that's only if these are perfect pennies. But in the minting process, there can be imperfections. And those imperfections are enough to make them biased. So maybe it's 7 heads and 3 tails. So what we're going to do is we have 1,000 pennies, which is a really sizable statistical sample. And so we are sure to find at least one biased coin. So we're going to flip these over and over again and see if we can find any pennies that always come up heads. Heads is win and tails is lose. So as we're flipping, we're going to do one round of flipping here. We're going to flip all 1,000. I'm going to collect all of the heads in this blue bucket. Blue means win. And all the tails will be discarded into this orange bucket. Orange means lose. It also means tails. So, well, let's get this party going. We're done with our first round and look at this. Well, let me ask, how many coins do you expect out of 1,000 would flip to be heads? We counted it, and it came out to 494. Yeah, 494 coins flipped to heads. Well, we're going to keep flipping. We're going to do another round of flipping. These are our candidates for biased coins. Let's see what happens next. Okay, we finished round 2. And check this out. We now have 271 coins that were flipped heads twice in a row. So we've whittled out over 700 coins. Awesome. Oh, and in case you wanted to know, these all look to be 2022 coins. So, I don't know, is that focusing? Okay, good enough. So, in the name of science, these coins are basically the same. But we're still going to find the biased coin. Okay, so we're going to do a few more rounds and I'll update you on what we find. Okay, we've done 5 more rounds, and you're not going to believe this. we have 9 coins here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these coins have hit heads 7 times in a row. That is just crazy. We're going to keep flipping these coins. Are you ready? Here we go. Okay, everybody grab. Okay, I got 2. Ready? Flip! We're having a flipping good time. Okay, let me take the heads off the table.
The tails.
Whoa, look at that. Whoa, 1, 2, 3, 4, 5, 6 got eliminated. Oh, we're
3 heads.
Dude, this is crazy. 3 coins among 1,000. All right, which one is it going to be? You can have it. I don't get a flip this time. Flip. 2 heads. Tails. Heads. Heads. Woo. Okay, give me this tails.
Yeah.
This tails is gone. Okay, then there were 2. Okay. Flip! No! Oh, gotta redo it. If it falls off the table, I have to flip it again. You can't get it on the table. Well, this is man. Yay! Heads! Yes! That's it! Look, the other one got tails! Yes!
That's the one.
Okay, Okay, I'm going to touch this coin. My hand will stop shaking. Okay. Man, I got this flip heads 10 times in a row. I'm getting like these really big nerdy math chills right now. Nerdy chill. Yay.
Crazy stuff.
Okay, so some of you might not understand how rare this is. Come over with me back to the whiteboard and I will show you how awesome this is. What is the probability that this coin could flip heads 10 times in a row? Okay, if we assume that it is an unbiased coin, the probability is 1 out of 2, 1/2. And in order for it to flip heads 10 times in a row, the probability of that happening is, well, we raise that to the 10th power. And we get 0.976. Okay. Let me show you what that looks like on a normal curve. Whoa. Okay. 0.000976 is like all the way, it's this little tiny section right here. That's about, some people call that -3 sigma. And that is crazy. In statistics, if you can show that something is less than 5% likely to occur, that's usually a statistical indication that there is something special about that item. Our initial hypothesis is wrong. You remember we were assuming that it was an unbiased coin. Well, the fact that we got this monstrously low probability proves that this penny is indeed special. It is a biased coin. Okay, and what about the 18 counties that flipped? Let's assume that they are not bellwether counties. That means they have a 1/2% chance of getting it right. So what is the probability of 18 of them flipping? It's 0.000038. Okay, that is a ridiculously low number. You wouldn't even be able to see it on this graph. It's just statistically significant here. And that means that something is going on here. So isn't that cool? Now I think for the fun of it, I just want to keep flipping this coin and see how many times it can flip heads in a row. It's already been done 10 times in a row. I just want to check it out. What do you think? Yeah?
Yeah, let's find out.
Okay.
Bruh.
What? Wait a minute. It hit tails. Wait a minute. It just did 10 in a row and it hit tails. Well, we're okay because a biased coin doesn't have to hit heads all the time. It just has to hit heads most of the time. Let me write tails. Okay, well, we'll flip it again. The 10 times out of 11, it hit heads. We know it's going to hit heads this time.
I don't know about this.
Wait a minute. Okay.
Sides.
Switching up.
So maybe I'm not doing it right. One of you want to flip it?
Here, I'll show you how it's done.
Oh, that doesn't count.
It's gotta land on the table.
Has to land on the table. Oh, it's going to be heads. It's going to be heads. It's going to be heads.
I believe it.
It is.
Yes! See, I told you. Yep.
There it is.
Okay, so far it's only hit tails twice. Okay, you want to try flipping it?
Sure.
Let's do it 10 times. I want to show them that it's going to come out heads the rest of the time. Oh, do that again.
Not a good flip. There you go.
Oh no.
Okay, wait a minute. Okay, let me try this.
Oh.
What the heck?
Uh-oh.
We know it's like making up for other times.
Oh, there's a heads. There's a heads.
Okay, you know how to get heads. Okay, we'll let you do it again.
All right. Couple more heads coming right up.
Heads.
Yes!
You know, it's more of a penny than me.
Oh, nope, it hit tails. Okay, right now we got 3 heads out of 1, 2, 3, 4, 5, 6, 7, 8. Okay, flip it 2 more times.
You got it.
Heads.
There's a head.
Okay, who wants to do it the last time?
You got it.
Okay. Heads.
That's kind of crazy.
Okay, let's see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Okay. We are back to 50%. This coin. Okay, I don't understand. This coin did 10 times in a row. And now we just flipped it 10 more times and it's 50% exactly. Okay, I must have done something wrong with my math. Okay, cut. Well, sorry about the math mistake, but I fixed it. Well, just come over this way and I'll show you. So how do I explain this? Well, what I wrote is not wrong. If I take this coin and flip it 10 times, its probability of getting heads 10 times in a row really is that number. Let me round it up to 0.0001. That is 1 out of 1,000. But we didn't flip one coin, we flipped 1,000 coins. That means we would expect one coin to flip heads 10 times in a row. And that's exactly what happened. And in a way, we kind of already expected it. You remember how in the first round, it dropped from 1,000 to 494 coins. And that's about half. In the next round, the second round, it cut in half again, and then a half. So it followed the pattern that we expected. Because we were flipping 1,000 coins, we were basically asking the impossible to happen. And in fact, we can calculate the exact probability of this occurring. What you do is you take this number and we'll flip that. I'll do 1 minus that number. So we get 0.9999024. Okay, that is the probability that a coin does not flip 10 heads in a row. Okay. So, what is the probability that 1,000 coins do not flip 10 in a row? We can calculate that easily by raising that number to the 1,000th power. Is 0.376. That's probably enough right there. Okay, so that is the probability that 1,000 coins will not flip 10 heads in a row. So if we flip that, subtracting that from 1 again, we get 62.4%. That is the probability that at least one coin will flip at least 10 times in a row. That's crazy. By this point, you're probably guessing that I messed up the math on purpose earlier. And yes, I wanted to capture the essence of the mistakes people often make when they present these bellwether arguments. It's an example of using math that looks correct on the surface, but applied incorrectly. It's something called survivorship bias. That's when you hone in on a small group of items that look like they're performing well. But if you were to do the math correctly, then you would see that it's just random noise that naturally rises out of the fact that there are a large number of data points. So, does this not convince you? How about this? We not only flipped to see heads come up 10 times in a row, we also took the coins that flipped tails in the first round, and we kept flipping those. And we did it repeatedly, and we were able to get one coin to flip tails 9 times in a row. And then we took that coin and we flipped it 10 times in a row just to see how it performs. And it got exactly 50% tails. So it was another case of a coin going from 9 times in a row to 50-50. Exact same thing. And still not convinced? Well, I challenge you to try this experiment at home. It's $10 and go get 1,000 pennies and start flipping them. Do the same thing I did. It will be a fun family event. And see if you get the same results. Still not convinced? Well, let me try another analogy. Let's say that we're at a baseball game and we have 1,000 people in this section in the stadium, and someone hits a pop fly, and here it comes. It's headed straight for the section. So what are the chances that I'm going to catch that ball? Well, there's 1,000 people, so it's 1 out of 1,000. That's a 0.1% chance I'm going to catch the ball. It's not looking very good for me. But look at the ball. What are the chances it's going to land in that section? It's practically 100%. It has to land somewhere in the stands. Someone is going to catch that ball. And that one person is going to get lucky. And so, how does it go from 0.1% to 100%? It's all because we have a large number of data points. The impossible becomes possible. Now, what about that guy that catches the ball? Is there anything special about that guy? Not really. It's just dumb luck. Okay, but what about our bellwether counties? There are 3,143 counties in the United States. And the one county that was correct from 1980 to 2020 was Clallam County in Washington. That is the furthest west county that you can go in the contiguous 48 states. Well, let's take a closer look at that county. They've had 33 elections, and they were wrong in 1976, 68, 16, 12, 96, and 62. That means they were correct 27 times out of 33 elections. That's about 81%. So that's pretty impressive. Maybe they are a bellwether county. How about we do the math, the same math that we did with the coins? How about we do it to this county and see how likely this scenario is? Well, to calculate this, it's a little beyond the scope of this video, but what I'll do is I'll calculate the probability of being 0 wrong, 1 wrong, 2 wrong, all the way down to 6 wrong. and we're going to add those up. So I've calculated those probabilities. For 0 wrong, I've rounded it to 5 decimals. You can see it's basically 0. It's not going to happen. Exactly 1 wrong, again 0. Just 2 wrong, 0. 3, 4, also 0. 5 wrong, we start to see it 0.00003. 6 is 0.00013. We add it up. 0.00016 is the probability that one county will have 6 or less wrong. That is pretty small. That's even more unlikely than flipping 10 coins 10 times in a row. That's very small. Okay, but we have 3,143 counties to deal with, so we're going to flip it just like we did with the coins. So 0.99984. So I did 1 minus that number. That is the probability that one of the counties is more than 6 wrong. So what's the probability that 3,143 counties are more than 6 wrong? All we have to do is raise that to the 3,143rd power, 0.60. If we flip it again, 40%. That is the probability that at least one county is 6 or less wrong. Isn't that amazing? We calculated it with just one county and we get this incredibly low probability. But when we look at all 3,143, it raises to 40%. That is within the realm of possibility. And that is the beauty of survivorship bias. That is the baseball landing in a crowd of people. The one person that gets lucky enough to catch the ball. And there's nothing special about that person, only that they're lucky. And likewise, there is nothing special about Clallam County. It's dumb luck. It is what it is. And I hope you've enjoyed this special mathy experiment. And I'll see you again here on Always Be Better.